number of times we come across spring with spring constant K. So what does it mean? What is the meaning of spring constant? We come across various kinds of springs. Some are short, some are long, some are thin, some are thick. But how we differentiate between these springs more on scientific basis? That is, over there we talk the spring constant. We use a term that is spring constant. If this is a spring and we say its spring constant is suppose 100 Newton per meter. What does it mean? It means if we want an extension of 1 meter, extension or compression, that is deformation, if we want a deformation of 1 meter in this spring, we will have to apply a force of 100 Newton onto this. Let's say there is this spring of spring constant 100 Newton per meter. Let's understand it. And over here we have a small mass. All surfaces, they are frictionless or so. It is 100 Newton per meter. It means when there is extension or compression of 1 meter in this will apply a force of 100 Newton, which is called a restoring force on that. Now let's say what we do is we start applying force onto this block. Initially there is no extension, no compressions on this, so this is more or less relaxed. As soon as we apply a force onto this, so obviously there is some extension produced in this. Let's say now extension is half meter. From here to here it has gone for around say half meter. So this is extension of half meter. So extension is half meter. So for every 1 meter there is a 100 Newton force is generated, it is produced, it comes into action. So if it is half meter, so it means now onto this a restoring force of 50 Newton will be applied, and we are applying a force now this way. If our force is equal to 50 Newton, we'll stop over here. We will not be able to stretch it further. So if we are applying right now a force of 50 Newton, this block will be over here, that is net force is equal to 0. This force is going to be balanced by this force, that is 50 Newton, which is generated within spring only. If this force is greater than this force, so certainly this will move in this direction. If it moves in this direction, then certainly there is going to be some more stretch in this. The restoring force will also increase. And in case we are applying a force of 100 Newton, then now what is going to happen is, that is, this reaches over here. So from here to here, now this is 1 meter extension. If 1 meter extension is there, so now if 1 meter extension is there, so in this situation, the spring will apply a force of 100 Newton. And in case we are also applying force of 100 Newton, so now we'll stop over here. We'll not be able to stretch it further. We'll not be able to pull it further. If we want to pull it further, then we have to increase this force. So from here, let's say even from units only, that is 100 Newton per meter, that is for every 1 meter deformation, a 100 Newton force is required. So it means that is for deformation of 1 meter, that is be it elongation, be it compression, we will have to apply 100 Newton force for every 1 meter deformation. This is also expressed as F is equal to minus Kx, that is this is called restoring force. If we are applying a force in this direction, the restoring force is in this direction. Displacement is in this direction, restoring force is in this direction. If we are compressing it, the compression is in this direction and this is going to push it this way, the restoring force is in this direction. So restoring force and deformation, they are in opposite direction, that is the only meaning of minus. Otherwise F is equal to Kx, that can give you the magnitude of force. Many times I have found the students getting confused if we say that is there is a spring of spring constant 100 Newton per meter and 100 Newton is being applied onto this end and 100 Newton is being applied onto this end. Then what is the extension on this? Many times students say that is net force is equal to 0, so that's why there will not be any extension. And some students they say that the force is 200 Newton, so 200 is equal to, that is F is equal to Kx or minus Kx. F is equal to 200, this is equal to 100 into X, so they say X is equal to 2 meter. That is extension is going to be 2 meter. Let's understand where the mistake is being committed. To understand this, let's fix it to a wall. This is fixed. This is natural length, and now it has been pulled from here natural length and the length is being increased. There is a stretch. As a result, this stretches and there is extension, and now through my hand I am applying a force of 100 Newton onto this, and this is applying a force of 100 Newton onto my hand, right? To every action there is equal and opposite reaction. Through my hand I am applying a force of 100 Newton. As a result, there is some stretch in this, and we know this is going to be 1 meter. There is no confusion in this because F is equal to Kx. So F which is being applied over here is 100. Spring constant of this is, there is no confusion, that is we are taking this as 100 Newton per meter. So K is 100 Newton per meter into X. So this implies X is equal to 1 meter. Simple thing. Now let's draw the force diagram of this. If we draw the force diagram of this and this wall, while doing Newton's laws of motion, we have done plenty of times, that is tension is always outwards for the free body which we are considering. Also, if we consider this as free body, then this T is in this direction. So for this T has to be in this direction. Both the T, they cannot be in the same direction, because ultimately this is not accelerating. If this is not accelerating, it means the net force is equal to 0. That is 100 Newton is this way. So this has to be 100 Newton. And who is applying this force 100 Newton on this? That is through this. This string is pulling this wall. This string is pulling this wall outwards with a force equal to 100 Newton. And to every reaction there is equal and opposite reaction. So this in turn will experience a force 100 Newton in this direction. So over here what we see is, this is a string which is attached to a wall. 100 Newton is being applied over here, and we know there is going to be extension of 1 meter using F is equal to Kx. F is equal to Kx, we know that is extension is 1 meter. But now if we delve deeper, we draw the free body diagram of this. So it means this is equivalent to, this free body diagram is equivalent to, that is 100 Newton force is being applied this way, 100 Newton force is being applied this way, and there is extension of 1 meter only. So extension is going to be 1 meter. So when we say F is equal to Kx, it is F is the force on both the ends of the spring. So if this is a spring, once again we are taking K as 100 Newton per meter. Over here we are applying 200 Newton, and over here we are applying 200 Newton. So when we apply F is equal to Kx, or F is equal to minus Kx, so F is in this case is not going to be 0, F is not going to be 400, F is going to be 200 only. So 200 is equal to K, K is 100 into X. So X in this case is going to be 2 meter, that is it will stretch by 2 meter length. When we did work, energy and power, over there also we found that is what is the potential energy which is stored in a spring. We know that is a force which was being applied over here. This was a variable force, that is F is equal to Kx, that is a variable force. As we try to pull it, the restoring force is increasing onto this, that is spring constant is K. So as a result, this force is variable, and when the force is variable, then certainly we have to use the calculus methods to find what is the work done. Over here, if there is force is there, and let's say at this instant, there is some extension in this spring, there is some extension. So as a result, this is applying a force Kx onto this, right? Onto my hand, this is applying a force of Kx in this direction, and through muscles, we are also applying a force Kx in this direction, right? And because now X is varying, so force is varying. So now what we do is, that is we move this end by a very small distance dx. We are applying a force in this direction, dx is also in this direction. So the small work done, differential element of work which is being done is F dot dx. For this small element of dx, the force almost remains same. What is force? Force is, that is K into X dot dx. Now we are applying force in this direction, dx displacement is also in this direction. So the work is Fs cos 0. Cos 0 is, that is we know, equal to 1. So it becomes Kx dx. Let's say we take the limits when the x has gone from 0 to x. So this is dw integral is going to be this much. So we had done work is equal to K is constant. So this x dx comes out to be x square by 2. Limits 0 to x only. So this comes out to be half Kx square. So this is a result which you can use for the potential in the spring. You can use this result, that is half Kx square is the potential energy stored in a spring where x stands for the deformation, be it elongation or be it compression.